We'll pick up where we left off when we have an equation for a surface, and we rewrote it in the 3 different coordinate systems. So we have it in Cartesian, and then we rewrote it into polar, and then we rewrote it into spherical. Going from one coordinate system to the other, we're using the triangle to do our change of coordinates. If you want to refresh your memory, it's under change of coordinates and the equation form. That's the video where all this is derived. But we'll assume you remember, and we move on. There's no obvious way to isolate a variable, so I have to see what it looks like to try and break it into cases. The easiest way to look at it, ZR plane. So I have my radial axis, my vertical axis that is spun around with theta. So I can take a 3D shape and I'm looking at a radial cross-section. So looking at the polar form or the spherical form, I can graph it. Z is just a function of r. Z squared equals r squared, so Z is plus or minus r. That radial axis gets swung around with theta, and there's my surface. It's a cone. So it's really 2 surfaces. I have an upper cone, and I've got a lower cone. Z equals r, that's my upper cone. And then Z equals minus r, that's my lower cone. Let's take a look at how spherical works, because that equation doesn't look the nicest. But it's not too bad, because I've got a rho on both sides. Rho is positive and non-zero, so I can divide both sides by it. Get rid of that. Sine squared is cosine squared. I can collect it together as tangent. Now the variable appears once, and I can solve. But again, it's 2 cases, plus or minus 1. Phi is only in quadrants 1 or 2, and so inverse tangent will work just fine. Although you have to know to modify the negative things by adding pi to it. So if your calculator gives you a negative answer, you got to add pi. Now we'll look at our sketch in the ZR plane, but using this spherical description. R, my radial axis, Z, my vertical axis, theta, swing it around in space, phi equals 0, that's straight up, and it drops down. 90 degrees, phi over 2, and 180 phi equals pi. And then we're done. Pi over 4, there's my upper cone. And then 3 pi over 4, there's my lower cone. Before we launch into parameterization, I want to review change of coordinates again. So when I write the x equals x and the y equals y and the z equals z, what I'm saying is nothing's happening. When I draw this triangle, now we're going to convert x's and y's into r's and thetas. This is giving me a transformation. So if I gave you the polar coordinate r and theta, I output the rectangular coordinates x and y. This is change of coordinates. R theta in, x, y out. Polar to rectangular change of coordinates. And we always want on the left-hand side x, y, z, because that's our parametric form. Our parametric form is always in Cartesian coordinates. So now I'm going to do it again to go to spherical. Instead of going in one fell swoop, it's always best to go this piecewise approach. After a while, you'll get you'll get the swing of it, but for the first couple times, you definitely want to do this exact thing. Cartesian to polar, polar to spherical. R is being replaced by rho sine phi. Now rho phi and theta are input, x, y, z is output. So it's a transformation from spherical coordinates to rectangular coordinates. Finally, parameterization. We get our equation for the surface in the coordinate system that it's expressed in. We'll just do polar right now. And then we'll convert. For conversion, remember, on the right-hand side is what we're substituting the equation in. And the left-hand side is the output of that system. Substitute on the right-hand side. So my default parameterization two parameters, x and y for the default, two parameters, r and theta for the polar. One surface is always one equation or two parameters. Now we'll do the spherical. My equations in rectangular coordinates, my equation in polar coordinates, and my equation in spherical coordinates. I substitute the equation into the spherical coordinates, which are on the right-hand side of your coordinate change. Get my parametric form, because remember, the spherical coordinates are your input, and your rectangular coordinates are your output. That's parameterization. Whatever coordinate system you're coming up with, that's your right-hand side, that's your input. Rectangular coordinates, left-hand side, that's your output. Two parameters, rho, theta. So three different parameterizations for the surface, depending on what you want to do.